And here's the crazy part. GPT-4, the model behind ChatGPT, is rumored to have cost over $100 million just to train. Can you imagine the infrastructure needed to burn through that much compute?
$100 million? That's astronomical. So we're not just talking about throwing a few GPUs at a problem anymore. What actually breaks down when you're scaling to that magnitude?
Exactly. Think about it this way. Training a model that size on a single machine would take literally centuries. Even on a small cluster, it's still impractical. The real challenge is orchestrating hundreds or thousands of machines to work together seamlessly, sharing data and model updates without bottlenecks. If you get it wrong, you're not just wasting time, you're burning a fortune in electricity and cloud compute.
Okay, so the cost is the immediate pain point. But what are the engineering problems that cause those costs to balloon? Is it mostly about network bandwidth, or is there more to it than that?
It's a perfect storm of challenges, honestly. Network bandwidth is a huge one, absolutely. But also think about data synchronization, fault tolerance, and the sheer complexity of managing such a massive distributed system. Let's dive into how they actually do it.
Sounds good. Where do we even start with something this complex?
Let's start with data parallelism. It's the most straightforward approach, conceptually. Imagine you have a huge dataset, way too big to fit on a single machine. You split that dataset across multiple machines, and each machine trains a complete copy of the model on its portion of the data. At the end of each training step, the machines synchronize their model updates.
So each machine has the full model, just a slice of the data. But doesn't that mean you're duplicating the entire model across every machine? That seems incredibly wasteful, especially when you're talking about trillions of parameters.
It does sound wasteful, and it can be if the model is large, but the beauty is in the simplicity. Data parallelism is relatively easy to implement and debug. Think of Netflix recommending movies. They have a massive user base and viewing history. They can split that data across hundreds of machines and train their recommendation models in parallel. Each machine learns from a different slice of user behavior.
Okay, that makes sense. So Netflix is using data parallelism to handle the sheer volume of user data. But what about when the model itself is too big to fit on a single machine? That's where model parallelism comes in, right?
You nailed it. That's when things get really interesting. Model parallelism is where you split the model itself across multiple machines, so each machine only holds a portion of the model's parameters. Now here's the crazy part. When you feed data into the model, it has to be passed between these machines, layer by layer.
Wait, so the data is flowing across the network within a single forward or backward pass? That sounds like a communication nightmare. How do they even manage that?
It is a communication nightmare. That's where the real engineering magic happens. They use techniques like pipeline parallelism, where different machines work on different stages of the model simultaneously. Imagine an assembly line where each station performs a specific task. One machine might be processing layer 1, while another is processing layer 2, and so on.
Okay, I see. So you're overlapping the computation to hide the communication latency. But what about the overhead of constantly transferring data between machines? Doesn't that become a bottleneck eventually?
It definitely can. That's why they invest heavily in high-bandwidth, low-latency interconnects between the machines. Think about Google's TPUs, for example. They're specifically designed for these kinds of matrix multiplications and have incredibly fast interconnects. They're not just using off-the-shelf network cards, they're building custom hardware to optimize for this specific workload.
So custom hardware is a key piece of the puzzle for Google. Are there software optimizations as well, or is it all about throwing more hardware at the problem?
There are absolutely software optimizations. Techniques like gradient accumulation, where you accumulate gradients over multiple mini-batches before updating the model parameters, can help reduce the frequency of communication. It's a trade-off between communication overhead and memory usage.
Gradient accumulation. So you're essentially amortizing the communication cost over multiple steps. What's a real-world example of a company using model parallelism at scale?
Meta is a great example. They've published extensively about their work on training large language models using model parallelism. They've developed custom frameworks and libraries to manage the complexity of distributing these massive models across thousands of GPUs. They have to, given the scale of their AI ambitions.
So we've covered data parallelism and model parallelism. Is there anything else beyond those two? It feels like we've already hit the limits of what's possible.
Wait until you hear this. There's also something called tensor parallelism. It's a more fine-grained approach to model parallelism, where you split individual tensors, the multidimensional arrays that hold the model's parameters, across multiple machines.
Okay, now you're just making my head spin. So instead of splitting entire layers, you're splitting the matrices within those layers. How is that even feasible?
It's incredibly complex, but it allows for even greater scaling. Imagine a single matrix multiplication being distributed across multiple machines. Each machine computes a portion of the result, and then they combine their results to get the final output. This requires very precise coordination and communication, but can unlock significant performance gains for extremely large models.
That sounds incredibly difficult to debug. What company is brave enough to actually use tensor parallelism in production?
OpenAI is rumored to be using tensor parallelism extensively in their training of GPT models. They need every ounce of performance they can get to train these massive models within a reasonable time frame. Remember that $100 million training run? Tensor parallelism is likely a key enabler.
Okay, so OpenAI is pushing the boundaries with tensor parallelism. But doesn't all this distribution introduce a ton of new failure modes? What happens when one of these machines goes down mid-training?
That's a fantastic question. Fault tolerance is absolutely critical. They use techniques like checkpointing, where they periodically save the model state to persistent storage. If a machine fails, they can simply restart the training process from the last checkpoint.
Checkpointing. So it's like saving your game progress regularly so you don't lose everything if the console crashes. That makes sense. But doesn't checkpointing add overhead as well?
It does, but it's a necessary evil. They optimize the checkpointing process by using techniques like asynchronous checkpointing, where the checkpointing happens in the background without interrupting the training process. And they use distributed file systems like HDFS or cloud storage solutions to ensure that the checkpoints are highly available and durable.
So it's a constant balancing act between performance, communication overhead, and fault tolerance. It sounds incredibly complex. What's the biggest mistake engineers make when trying to implement distributed ML training?
Here's where it gets interesting. Many engineers focus solely on the computational aspects and completely neglect the data pipeline. They assume the data will magically be available on all the machines at the right time, but in reality, the data pipeline is often the bottleneck.
Ah, the classic garbage in, garbage out problem. But now it's slow data in, slow training out. So what should engineers be doing differently?
Exactly. You need to invest in building a robust and efficient data pipeline that can handle the massive data volumes and high throughput requirements of distributed ML training. Think of Uber, for example. They have to process massive amounts of location data in real time to train their models for ride-hailing and routing.
Okay, so a strong data pipeline is crucial. What are some other practical takeaways for engineers working on distributed ML?
Here are 3 things you can do today. First, profile your existing training pipeline to identify bottlenecks. Don't just assume the GPUs are the problem. The data loading or communication might be the real culprit. Second, experiment with different data parallelism and model parallelism strategies to find the optimal configuration for your specific model and hardware. There's no one-size-fits-all solution.
And the third?
Third, embrace infrastructure as code. Use tools like Terraform or CloudFormation to automate the provisioning and management of your distributed training infrastructure. This will make it much easier to scale your training jobs and recover from failures. Think of it as infrastructure origami, folding and unfolding your compute resources as needed.
Infrastructure origami. I like that. So profile, experiment, and automate. Solid advice.
Absolutely. And remember, scaling distributed ML training is not just about throwing more hardware at the problem. It's about understanding the trade-offs between computation, communication, and fault tolerance, and designing a system that's optimized for your specific needs.
Right. You need to be an architect, not just a coder.
Exactly. And in the end, it's about building systems that can learn faster and more efficiently, unlocking the full potential of AI.
So it's not just about training bigger models, it's about training smarter.
Precisely.